Hello, everyone. Welcome to this very first Model AI webinar, which is going to be about game playing bots. So for those of us who don't know us, Model AI, we are a startup out of Copenhagen. We're a company dedicated to AI and machine learning. Now, this webinar that we're having today is the first in what is hopefully going to be a longer series of webinars. In terms of what to expect, we'll be starting the session today by talking a little bit about game playing bots, and then we'll have a QA session afterwards. The two hosts that you have here today is myself. I'm speaking now. My name is Christopher Holmgaard, and I'm a co-founder and the CEO of Model AI. Before we started Model AI, I was a game developer in a game studio that I co-owned called Die Gute Fabrik. And simultaneously, I did a PhD in AI for games and worked as a researcher and professor in that, working on various kinds of machine learning and different kinds of modeling player behavior. And before that, way back when, I actually started out, before coming into games, I started out in psychology and psychometrics. And I'm joined today by Niels Justesen, who's an AI researcher and developer here at Model AI. And I don't know, Niels, do you want to say hi and just introduce yourself?
Yeah, sure. Well, hello, I'm an AI researcher and developer at Model AI. I recently finished my PhD at the IT University of Copenhagen, and before that I was a software developer for around 5 years. And I'm also organizing an AI competition in a board game called Blood Bowl, which is really difficult. Not organizing it, but playing it. And the competition is called Bot Bowl.
Yeah, thank you so much. I also wanted to say that one of the reasons that we're doing this as Model AI is, of course, that we want to talk about the work that we do, but also generally we just want to create a forum and sort of spread the good word about what AI and ML can do for video games. So we'll just start out by talking a bit about game playing bots and sort of trying to paint our perspective of how we understand what game playing bots are and give you our perspective on how we go about building them. We'll talk a little bit about use cases for game playing bots in game development, and I'll be talking chiefly about that. And then I'll be handing it over to Niels, who is our resident expert in all things cutting edge in terms of algorithms for game playing bots. And we'll try and sort of cover the space of what's available there in game development. Finally, we'll also be showing a small sneak peek of a product that we're working on here in Model AI that we call the Model AI Play Flexible Play Trees, which is basically a system for learning from player behavior and then using it for various purposes in Engine. And we are working on a number of things here in the company that we can't show yet. So what you'll be seeing today will mostly be implementations in open source frameworks or internal tech demos. But if we keep on having these events, hopefully in a couple of months we'll be able to show you some of the cool things that we've been working on behind the scenes and some of the things that we've been doing with collaborators as well. So with no further, I should also say, sorry about that, but if you have questions, any questions along the way, there are quite a few of us here today, so please feel free to ask any questions you might have in the Zoom QA section. Just put them in there in the box. Some of them we might be able to answer from the team. We have Daniela and Benedicta with us, and they might be able to answer some of them on the fly. And if we can't, we'll try and get around to as many of them around the end of the webinar as we can. So yeah, let's go. A little bit more about Model AI and what we do. Fundamentally, our mission in Model AI is to bring and make AI and machine learning available to as many game developers as possible. Now that means talking about our own stuff, of course, and we love to work with game developers who love to work with us. But also generally, we just want to make sure that there's a space where people can communicate about this. And that's also why we sort of have a commitment to talking about the methods and some of the research and development we do. So even if you don't end up working with us, if you end up building your own or you work with some other provider, we think this is interesting to build some awareness about in the industry and in academic spaces. Specifically in Model AI, we focus on delivering 4 things to game developer, all based on sort of like one single integration of a data collection module. And what we offer developers sort of like runs the gamut from what we call model experience, which is making sense of how players are enjoying a game and what they're doing. Sort of like the psychological profiling step for game analytics, you might think about it that way. Then using the same data to learn bot behaviors, which is what we'll be talking about today. But also using the same data to maybe find behavior that's a little bit different from what you were expecting, which might indicate that people are cheating or that they're using different kinds of bot systems. Finally, we also do work in machine learning content generation, machine learning driven content generation, where you can often use the bots that you have generated from player data. Well, you can use that to evaluate content that's coming out of various content generation systems. But the topic for today is obviously model play. So or in general, game playing bots. So let's dive right into that. I think one thing we should take care to determine when we talk about game playing bots, and specifically when we're talking about bots that leverage machine learning, what do we really mean? Because if you look at sort of like what goes on in the media and goes on in the literature, there are sort of different groups of people that all use or maybe sometimes they're the same people. But there are different applications of game playing bots and different meanings of game playing bots that sort of like make sense in different contexts in game development. Now, the first way you might talk about game playing bots, and I think that's what most people think about when you say game playing bot, is sort of like the bot as a game asset. So that means, the kind of bot that you encounter if you're playing a multiplayer game and you're playing a mix of humans and computer-controlled opponents, or NPCs. And there, of course, throughout the history of games, we've had sort of like a plethora of really cool examples of ways of implementing that. More recently, you might have seen some of the interesting developments that sort of like sit more in the AI research, pushing the boundaries of what you can do with AI and machine learning, where you start using bots as a way of performing up against an AI benchmark. And there can be systems like Deep Blue, AlphaGo, AlphaStar, OpenAI 5, all these different new, really monumental sort of like accomplishments in AI that we've been seeing in recent years, especially as deep learning has been coming into its own, and has been coupled with things like stochastic tree search and simulation to power new advances in game AI. Now, the third place where we can talk about bots is at development tools. And this is really a place where nobody's really seeing the asset necessarily, and you're not using it to be the benchmark, but you're using bots as a tool that very pragmatically is helping you as a game developer to build a better product and have more confidence in what you're building. And what we think at Model AI and what we're working on internally here, well, we think that there is a special opportunity in using player data and using methods like imitation learning and reinforcement learning, coupled with more classical methods, to take some of the cutting edge research that's been happening in the efforts to beat these AI benchmarks, and use that, combine it with more classical techniques, and give developers new opportunities for build bots that either play like players, maybe get a little bit of a better game feel than you would get from standard scripted bots, or build better tools that help developers in their development process. When you're doing that, of course, you sort of like face a challenge, because as soon as we talk about learning from player behavior, we kind of like face a question like, which players do we choose to learn from? Because obviously what kind of data that we choose to collect is going to be paramount in shaping the behavior that our bots will end up having. There are different ways of addressing this problem, and sort of like the really classic one that most people on this call are familiar with are Bartle's player types, where Bartle, he divided players into sort of like 4 different fundamental categories based on what kind of experience they were looking for in the game. In Model AI, we approach this from a slightly different angle. We approach it from a psychological framework called self-determination theory, and specifically a version that was that expanded upon the basic psychological framework developed at Ubisoft into a questionnaire and a tool and a model called the Ubisoft Perceived Experience Questionnaire. Very great work. I definitely recommend checking it out. It really breaks the interest of the player and the experience and motivation of the player into four fundamental categories. And the four categories are sort of like how interested is the player in competence. So that is in really being good at the game and showing that they're the best competitiveness. The second dimension is autonomy. How much do I play video games in order to enjoy freedom, in order to be able to express the kind of behavior that I want to express? Relatedness is very much the social component. How much do I care about connecting with other players in my game, in the game that I'm playing? And presence, which is sort of like the addition that happened when this framework was adapted to video games, is the idea of being able to really sort of like feel yourself transported into the world of video games. And that's definitely a category that's important for me, but I don't know how often, like where you find yourself on the spectrum. And you'll typically find that people's motivations also vary across games. Now, what's really interesting about this model is that we don't have to put you in one distinct category, but rather we can use it to understand how much you load on each of these factors as compared to other players. In fact, we had the good fortune and the chance to have the Model AI team work with a team at Ubisoft to test this in practice. And this is one of the reasons that this sort of like approach is now underlying a lot of the work that we do at Model AI. Where for Ubisoft Massive's game The Division, we were able to collect both survey data from that game and collect gameplay data, or of course Ubisoft collected the gameplay data, but really model that in order to understand different groups of players and sort of like put them into different clusters and categories and directly relate what the players were doing in the game to what preferences they had and what they preferred about the game. So that's great. You can actually map. You can map from different kinds of game data in order to understand different kinds of player types and understand what different kinds of players care about when they play games. But what kind of considerations go before that? What do we need to think about before we set up a study like that? What kind of data do we actually need to collect from our game in order to enable this kind of psychological motivation modeling and profiling that lets us find the different kind of players that exist in our game? Well, naturally, that really depends on what kind of game we're talking about. If you consider a game like, for instance, chess, and you compare it to something like this is Unreal Tournament 3, or you think about a game like Forza Motorsport, or you think about something like StarCraft 2, these are all really, really different sort of like problems for the players that require you to make decisions at different kinds of levels. And well, the way that we approach it at Model AI is that we always say that, well, you should look at the actual design of the game and figure out what is a meaningful sort of like decision level. So whereas for a game like chess, it's pretty obvious that a meaningful decision is like every time you move a piece, you're making a really significant decision. It may be less clear for a game like Unreal Tournament, where you might have to think about, well, is an interesting decision that I move into a different part of the game, or is an interesting decision that I swap a weapon, that I choose to fire. Again, looking at something like Forza Motorsport, well, now we're down at a level where the decision making happens sort of like at two levels at the same time. There's some very detailed moment-to-moment calibration, and then there's questions of like planning your approach for the different curves. And of course, one of the hardest games in the world, StarCraft 2. Well, here we're looking at sort of like all of these different decision-making levels all happening at the same time. But we find when you're setting up sort of these tracking events in your game, when you're deciding like where are the important decisions, that it's helpful to think about your game along these three sort of like levels and say, well, what's important in the game that I'm looking to instrument? Is it at the strategy level and what are the important events there? Is it at the tactical level and what's important there? Or is it at the action level? Is this really just like a Twitch game? And what I really should be focusing on is collecting and sort of like storing each individual player action. But it doesn't really change the fact that sort of like the loop that you go through when you think about how will I go about collecting data from my game that lets me identify the different player types and subsequently use that for modeling and learning the behavior of different kinds of players. Well, you go through this sort of like these like 4 stages of defining where are the meaningful decisions in my game, how do I observe and capture these, how do I identify different kinds of players based on that, and then, of course, there's tricky, well, all of these are tricky, but the maybe very tricky bit is how do I learn to replicate it using AI and machine learning. And that sort of like also begs the question, where is AI and machine learning most useful? We are finding so far, in terms of like what I was talking about before, porting some of the methods that have been developed in research and development, and sort of like bringing them pragmatically into the space where they're sort of useful for day-to-day game development, either as assets for the game or for developer tools. Well, we're finding that the places where we're seeing that make a lot of sense is, especially if you're working on casual games, puzzle games, limited strategy games with sort of like a small decision-making space, driving games to the action games, and 3D action games. We sort of like have methods that fit well into that, and Nils is going to talk about that a lot more in just a bit. And when we consider sort of like harder games like strategy games and tactical games, it starts becoming not impossible, because obviously we've seen that with OpenAI 5 and we've seen it with AlphaStar, but it starts becoming difficult and expensive to use AI and machine learning still. But what that looks like in the future, that of course is it's hard to say. With improvement in methods, you might see these sort of like circles of application areas. And where does this kind of learning like fit into my development process? Well, what we've been seeing from the cases that we've been working on so far is that, well, once you have bots that are actually capable to a certain extent of replicating their behavior, well, this becomes relevant for quality assurance, where you can use it to maybe save some of your precious human QA resources and use it on problems that are harder than just testing the same thing over and over again. You might even be able to automate some of your QA processes and have them happen with, for instance, commits into your code repository. If you're interested in balancing, that's another good application area of bots. If you have a lot of different parameters that you need to check in your game, well, running simulations of that allows you to evaluate many different game configurations, which is something from our experience. We've worked with dev teams who would be spending 20% of their time 1 day a week in balancing their multiplayer games, and they managed to bring that count down significantly, because instead of scheduling meetings between two developers, well, now like one developer could play against the AI in order to balance the game, or they could even run it headless and in parallel in order to get many different evaluations, game configurations, without having a human player in the loop. And finally, of course, there's the place where most people again would think about bots, that is player-facing bots, where you can use this kind of learning behavior to determine the bot behavior for maybe simpler, or I wouldn't say necessarily simpler, but for certain kinds of games like we saw in the slide before, you can use it to determine your bot's behavior, either completely, or if you have a more complex or demanding game, partially. You can use it to keep up with player meta that develops by retraining models as new player data comes in. And something that's been going on, of course, in motorsport for quite a while with the driver tower models we have, but now we're seeing it in more and more games. And you can learn individual player styles to provide ghosts or shadows of individual players, which is a really cool mechanic to have in your game. You can sort of like make a copy of yourself and send it to a friend. So with no further ado, I'll hand over to Nils. This is just me trying to sort of like draw a shape of the space of what you can do in playing bots and AI and machine learning together. And now I know, Nils, you're going to talk a little bit about sort of like the details of some of the algorithms and some of the setups you can use to enable this kind of work. So I'll just try and hand over the hosting privileges to Nils here.
Okay, yeah, so I will walk you through some of the AI methods we use for creating game-playing bots. And I will also highlight some of the challenges there are, and present some of the approaches we do to overcome the challenges of each of the methods. So our toolbox, you can kind of separate it into two groups of methods. One method applies computation online, so as the game is running. So basically, whenever the bot takes a decision, it applies some computation to figure out how to behave. And the other group applies offline computation. So this can be a long training session before it's put into the game. And when it has learned to behave, you can put the bot into the game. And usually with those techniques, you use very little online computation when it's actually in the game. But obviously you can combine these different methods in various ways. So like the first and perhaps simplest approach is applying scripted behaviors, where it's up to the developer to put in the game knowledge into the bot. And this can be done with a behavior tree or finite state machines and stuff like this. So basically any method you have to put in and describe how the bot should behave. And this gives a lot of control for the developers. You can basically specify exactly how it should behave. But as the behavior grows in complexity, it becomes difficult to you kind of lose the control a bit because it can be a bit overwhelming to create this scripted behaviors. Sometimes you actually don't know how to describe a complex behavior in code, so that's a big challenge. It's also very time consuming to implement and definitely not automated because you need to have the game specific knowledge into the bot. The next group of methods is search, which applies this online computation and sees the game as a search problem. So among these algorithms, we have A-star, Minimax, Monte Carlo tree search, and even evolutionary search algorithms that can search forward using simulation of the game. Some advantages are that we can achieve optimal play in simple games. It doesn't use offline computation, so we can basically put in the algorithm without any training. And as long as it has access to the game as a simulator, it can do this forward simulation. It can work, and the good thing here is that as long as it has access to this perfect simulator, it can generalize and adapt to new changes in the game. So if you put in a new level and the simulator has knowledge of this new level, then it's able to play on it. And we see with some of the next methods that that's not always the case. And obviously, if the state and action spaces are too large, then we are not able to apply these search, at least on the raw action level, and then some challenges appear. So going into some of the machine learning methods, just quickly want to mention the idea of having a policy neural network. So you probably all heard about neural networks. And when it acts as a policy, it basically maps observations from the game. It could be the raw screen pixels, and map it to actions. And in this very simple case here in a racing game, it's mapped to the 4 different actions moving in the 4 different directions. And right now it's very popular to use these deep neural networks to do this mapping, where you feed in the observation to the neural network and the output of the network is what action it should take. And there are some different ways to design these observations. One way is to do raycasting. And in the example you see here, I'm just testing this raycasting system in a racing game where you can detect the other cars. And this worked quite well. But one of the downsides is that you have to go in and decide what kinds of objects the agent can see. So what we like to do is also to use pixel data directly because it's not specific to the game. We basically just take a camera and add to the agent without putting all this domain knowledge in. This agent here has learned in this first-person shooter game Doom, it has learned a pretty good behavior just from raw pixels. So this is reinforcement learning that I will also talk about next, and we see here that it's maybe not human-like in this exact moment, but it is a pretty good behavior. So one of the machine learning methods we have in our toolbox is imitation learning, where we map these observations to actions using a data set of expert demonstrations. So if we have the ability to record our players, we can learn a behavior from this data using supervised learning. So imagine that this data set could be the screen images from the game, similar to what the player sees, and then a label of what action the player took in that moment. And when you apply this supervised learning on this kind of data, it's also called behavior cloning, which is like the simplest variant of it. What you end up with is a policy that outputs a distribution over the actions. So in this case, with the 4 different actions, we see like percentages on each of the action. And this is kind of a mix of all the players we have in our data set. And we can, of course, sample from it. So sometimes it moves right, sometimes it moves left in this case. But it will still try to have this balanced or mix of all the players in our data. So one way to overcome this is a method that we have developed called behavioral repertoire imitation learning, where we can control different behaviors of the imitation learning bot. And here in the game StarCraft, we see that the bot has learned to create different army competitions directly from these expert demonstrations. And when we have the bot after the training session, we can control exactly how it should behave. And we did this by taking the data set and creating this behavior space based on how the player played in the game. In this behavioral space, we have separated the data based on the unit compositions. We see the data on the bottom right use heavy marines, and in the top left they use these mech hellions. And this is the coordinate in this space is an additional input to the training, and that's also how we control it in the end. So the last part of the 4 methods are reinforcement learning, where you interact and learn, where you learn through interaction with the game. So you observe, you get these observations from the environment, in this case the game, and you send actions back to the game. You also are given a reward, and this is very important in reinforcement learning, because in some games you have a score. For example, in this game Breakout, you can use the score directly to reward the agent, which will guide the optimization easily. But in other games, you will only know if the agent is doing good at the end of the game, based on whether it won or lost. And here we have some tricks to use reward shaping, applying our domain knowledge to gradually guide the agent during the game. But that part can be a bit tricky. Another challenge is overfitting in reinforcement learning. So in this game called Zelda, where the agent has to pick up a key, avoid or kill some monsters, and then exit through a door, we can see that we can easily learn a behavior that can complete this level we see here. But if we then, after training, test it on a very simple but also different level, it doesn't behave well. And it's, in this case, actually worse than an agent taking completely random actions. So this is a clear case of overfitting. And one way we overcome this issue is to implement or to apply procedural content generation. So as the agent is training, we continuously create new levels for it to see. And if we create enough levels during the training session, it will be able to generalize to new and unseen levels. And actually the levels you see here are not introduced in the training. We also found that in some games, the approach doesn't work directly. We actually had to scale up the difficulty of the generated levels. So starting out with simple levels like these, and as it learns, we increase the difficulty of the generated levels. As Christopher also mentioned, there are some games, for example, real-time strategy games, where it's not really feasible to apply these end-to-end reinforcement learning methods. At least it's very costly. But one method we have had some success with is to combine some of these methods. So start out with a rule-based system, and then replace some of the parts with neural networks. And we had some success in StarCraft replacing the strategy module with a neural network. Another approach, because imitation learning requires a lot of expert data. So, but for QA testing, we can actually use just one recording of a player and use that in various ways. So in the video here, we see that we can replay an action sequence, and we can use this replaying play trace. We can replay the play trace to see if we can still complete a level. So imagine that we have developers changing this level all the time. We can on a server run this action sequence all the time to test if the level is still completable. And this works well if the game is deterministic, but if not, and in this case the character and the enemies spawn in different areas whenever you load the game, then replaying the action sequence obviously doesn't work. I'll show you a few examples here. But what we have been working on is a flexible play trace system where, using this one play trace from a recorded player, we can actually learn a behavior that is similar, but allow our machine learning methods to diverge a bit from it. So we see here an agent that has learned to shoot to overcome some of these randomness, overcome some of the randomness in the level, but still it stays close to the recorded play trace. And we also did this in a racing game. And you see the green circle is the recorded player, and it diverges a bit from it. And in some cases, it actually finds some very interesting ways like this to get through the level. And now I'll try to pass it back to Christopher.
All right, thanks. And we're coming up on time, so I just wanted to say what we were hoping today was just to show a few ideas on what you can do with this kind of approach to AI machine learning. If you are interested in learning more, or if you have a game where you think this would be a good fit for using maybe the flexible play trace for your QA processes, or you'd be interested in doing something a little more involved for balancing your game, or maybe even going for player-facing AI. The three things tend to build nicely on top of each other. So you maybe start with QA, and then as your game develops, you go to balancing, and then you go like once you're satisfied with the behavior of the bots, you consider including them in your game instead of sort of like a more classical scripted bot. Well, we are at the moment we have we have 3 different plugins in various stages of development that are kind of like in alpha that we can work with people to implement. If you're using the Photon Quantum engine, then well, first of all, lucky you, we really like it. But if you're using that, we have pretty good integration facilities for that, and putting the data collection right in your game using sort of like a prefab and integration. If you're using Unity, most of the examples that you saw here, or actually all of the examples from us, were made in Unity. We have an early alpha integration for that as well. And the next one on our roadmap is Unreal Engine. So if any of this seems interesting to you, please do get in touch. And I'll just finish off before we go to QA by saying thank you for your time. Here's a video of 2 bots in a fighting game running in Photon Quantum, trained using reinforcement learning. I hope this was a good experience. We really would appreciate any kind of feedback on these events. Please get in touch on our Twitter or send us an email at webinars@model.ai. And next Tuesday, we'll be talking a bit about our experiences and well, I'm not sure I dare say best practices, but let's say our opinions on how you can do your game architecture for AI. And in the following Tuesday, we'll be talking about different approaches you can take to catch cheaters and defeat bots using machine learning. So thank you so much. We also have a newsletter on our webpage at model.ai, modl.ai. And thanks for joining and thank you for your time. We'll step over to the QA program. Okay, so taking this from the top, there's a question here about are there any good examples for ghosts or shadows in existing games, except maybe Echo. Yeah, I completely agree that Echo, especially from a game design perspective, is a fantastic example. And it's a really, really smart way of using this kind of like layer imitation. I don't know how the implementation is actually done if you use machine learning, but it's from a game design perspective, I think it's really, really well done. Then I think there are a number of fighting games that use this as well. Killer Instinct, I believe, and Samurai Showdown. And I've also heard about a number of other sort of like larger games that use it for bits and pieces, especially sort of like in the part of the game where the game feels really important. So it's where you want to make sure that you get the kind of like variation in player actions that can be hard to script your way out of. So in the sort of like very second to second part of the game. So that was one question. You're asking, this is probably one for you, Niels. One on flexible play traces. Do you use one expert recording?
Yeah, I see a few questions on that, so I can answer that. So we have about whether we use one expert recording or more. We have experimented a lot using just one, because this would be like the optimal case, that the developers only record one playthrough and then we can learn a bot that plays similarly. But we also found that using more is better, of course. But we have tested a lot with just one playthrough. And then can you go in more depth about how it works if it's learned? So the flexible play trace agent is learned, and it's applying imitation learning and reinforcement learning to imitate the play trace that is recorded. So in one sense, or to say this differently, it's rewarded for staying close to the recorded playthrough, basically.
Should I take the next one? So here's the question. Could we mention concrete examples of games, or at least game genres, where we've had success with? And I am not able to mention any specific games yet. Hopefully we will be in a few months. But we've worked on sort of like PvP arena battle games. So games where you have direct unit control over a team of units in sort of like a top-down game where you have one player versus one player, and they each control 4 different units. In this case, for mobile games, we're drawing on the screen, where we saw some of this work pretty well. Internally, we've been applying it to, we have a number of puzzle games we're working on internally the racing game that you saw as well. But currently, we are chiefly with the customers that we're working with. We're chiefly working on 3D arena games, so games where you have sort of basically a big open space that you're moving around, and the challenge for the agent is to navigate that space and sort of like decide between objectives, but also at the lower level engage in sort of like um, interesting player behavior. So yeah, 3D action games basically, I guess is the short answer. The next one is how you pass computer pixel data to machine learning algorithm. Do you want to go in on that, Nils?
Yeah, I can do that. So I think that there is like two parts of it. First, you have to like extract the pixel data as the players are playing the game, and in game engines you can usually save the pixels from the camera that the player sees. So that part is pretty easy. And then when we have the data, the pixel data, it's also quite easy to pass it into our machine learning libraries as basically as floats or float values. Maybe you can also elaborate a bit on the question if it was unclear. I also see some questions about the behavioral repertoire method, so maybe I can answer that. The first question is how the behaviors are gathered. So along with the observation and action pairs, we usually have a bit more information about the player data. It could be information about the player, how much the player has played. It could be whether like what kind of objectives was reached during the game. And we can also extract some higher level behaviors based on the actions directly. And then we did that in StarCraft, where some of the actions are whether it builds a certain kind of unit, and we use those as our behavioral dimensions, basically. Can you elaborate on how the agent choose different behaviors during inference mode? Yeah, so during training, the behavior is an additional input to the neural network. So it's basically an additional label in the training set. And then during inference mode, so when it is applied into the game and has to take decisions, we can control this extra input. And since we defined this behavior space, we also know which areas of the behavior space, basically what those areas mean. So in the video I showed you, we could tell the agent, now you have to do a marine rush strategy.
Well, here's a different question, which is about model experience, and I think we're going to make that the topic of a later webinar on its own. But the attendee here is asking, what type of data does the search collect, and what is it used to make the model? And the person also asks how common is this type of data used and implemented in currently published upcoming games compared to gameplay bots? Okay. So for model experience, we typically look at sort of like event level or action level data, and we try to collect both. You can, for some games, it becomes infeasible to collect that data for all the players. And in that case, you might just want to sample it when you need it, or maybe only get the detailed data for sort of like a sub-selection of your players, depending on how many you have. But it would be any significant event. So let's say that we're thinking about a first-person shooter game. It would be switching weapons. It would be firing. If we could afford it, we might even gather the sort of like navigation of the interaction events, because that also becomes useful for the bots. But we would also ask the developers to tag different parts, meaningful parts of the levels. It can be as easy as putting in sort of like collision volumes in the level and say, oh, you're in the sniping zone, or you're in the arena zone. Just getting sort of like rough estimates of that, so you get a trace of not just what the player was doing, but also sort of like a semantic tagging of that, because it actually turns out that that's a really good way to like capturing player motivations. Then on top of that, what we typically do, so like a standard approach is to give the questionnaire to a sub-selection of your players. And in previous work we've done, it turns out that if you just survey, say, like 400 of your players with the questionnaire, that is typically, depends on the game, but that's typically sufficient to sort of like generalize to the rest of the player base. So for a small part of your player section, you collect sort of like both telemetry and you get the sort of like their subjective opinion about what they liked about the game. And then you generalize that to the rest of the player base where you just get the telemetry, sort of like the player doesn't see it. But then you use that to infer like what they would have answered to the question. Yep. Maybe related to that, there's a question about whether we use any kind of like objective measures, keystrokes, e.g. Heart rate, web camera, facial recognition, and eye tracking for measuring player experience and emotions. We've done it mostly in a research context, and I think there's especially I'm a big fan of eye tracking in particular. It's a really rich source of data. Also things like posture data, sort of like tracking player movement. EEG, heart rate can be a little more difficult to make sense of in context, I think. But at Model AI, we're chiefly focused on doing things that you can scale to most of your player base. So we're looking at sort of like objective measures as something that sort of like belongs more in the playtest lab. But if we were working with someone who would be able to deliver that data to us, we definitely, I think there's information there that you can include in modeling. It's just not the core part of what we're doing at the moment. Great. Well, there's a business one I can just grab in the meantime, or sort of like more a practical one. So model for the quantum engine, is it ready for production level games, terms and things like that? So I would say that we're at the alpha stage. So we're looking for some developers who would like to implement this sort of like with us and tell us what we should change about it and what works well and what doesn't work well. So we're some ways out there still, but it's where we're going on our roadmap for it. What about bots that play for experience? Which of the presented methods is a good fit? Oh, so this is basically a question that says, well, what about if I try to drive my bot's behavior to, as I understand it, to seek out a certain experience for in the game, in order to test if so if you had a bot already where you evaluate what the bot is doing, you can map it to what kind of experience that translates into, and now it's trying to optimize for that experience. I hope I got that correctly. What are your thoughts on that, Niels? Like, what kind of approach or algorithm architecture would you take to that?
Maybe one approach could be to collect some data of players that actually have that experience, and then use the observations that those players obtain during the game as kind of a reward for a learning algorithm. Yeah, that could be maybe one idea to do it.
I am working on using Gameplay AI to support players. AI as a coach, buddy, assistant system, if you will. Can you think of any projects I should check out? I suppose this is sort of like in the same category as sort of like the collaboration question. So that might be a good direction to go in as well. On the very sort of like research end of things, there is this is not reinforcement learning, but there is work going on in terms of agents based on empowerment principles. Two of our colleagues that I know that are working on that are Christian Güdelsberg, if I'm getting the name right, sorry, and Christoph Selke, where they basically build agents that attempt to optimize the empowerment, and by that meaning sort of like the amount of options that are available to other players. So imagine that you have an AI assistant, like a buddy, and the only thing that it's trying to do is sort of like make sure that you can do whatever you want. That's sort of like, right now I know it's been implemented as it's more of a search-based approach, but basically what the agent does in that case is that it looks ahead in time and it looks at sort of like what can I do to make sure that you have the greatest amount of freedom in the future, and in that sense, it tries to increase your empowerment. So that would be one concrete thing that might be worth checking out. I don't know if you have anything else for that one, else.
Mm, maybe like matching players in some way could be interesting here. If we can match a player with other players with a higher skill level but a similar behavior, it would be interesting to match them and you can learn from those players.
So yeah, with this, thanks so much for joining. We really appreciate so many people wanting to show up for this. Thank you from me. This was a little bit scary doing this. We had the microphone trouble, but we're glad that you all showed up. And thank you on behalf of the whole Model AI team.
Yeah, this was great. Thanks everyone.